So, as I said, the current assignment is a 2-week assignment, mostly just because we're where we are in the class, so it's not a particularly long assignment. But in any event, very good. All right, so what we're talking about right now, our goal for the next week or two is to talk about what in some sense is the core of quantum optics, which is understanding the distinction between what we call classical light and non-classical light and how we characterize it. And well, one of the reasons why this is subtle amongst many is that there can be randomness in our measurements. That's to say, our measurement outcomes are not completely predictable classically as well. So just because we see some random events, things that we don't have a good way of predicting, doesn't mean that that fluctuation, that random measurement is coming from quantum mechanics, right? There's classical statistical uncertainty too. And that's, so in order for us to contrast and understand what is a classical fluctuation versus a quantum fluctuation, we need to understand a little bit first about classical statistical optics, all right? So light sources, typical light sources around us, are not coherent light, okay? Which is to say that the electric field or magnetic field associated with the wave is a random variable. We don't have a perfect description of it. And the reason is because the sources that are radiating those fields are random in some way. We don't have full information about those radiators, okay? So a particular model of interest is thinking about a collection. I have many, many radiators that are, I think about as oscillating antennae, dipole antennas, which are oscillating at some frequency, but periodically there's a collision and that causes a jump in the phase, okay? That leads to, if I think about that, people talk about that in terms of thinking about that source as being collision broadened, okay? The term collision broadened makes what's being broadened here doesn't really matter at this point, but just as to hear some jargon, okay? But the bottom line is this: I have a collection, an ensemble of oscillators, are all oscillating with some frequency omega, but there's a random jump in the phase. We don't know exactly when it's going to happen, but maybe there's a mean-free path. There's sort of an average time. So there's some time over which we would say the field is coherent, but then it loses coherence, because when I look at the superposition of the electric field from all these radiators, they're going to have a random phase with respect to one another. Okay, over some time. Yeah.
But what are they colliding with?
They're colliding with each other. They're atoms. Each atom is radiating. It's a gas. They bump into one another, and or there's some radiators and there's other molecules. I mean, I'm thinking about a gas at the moment, but I could also think about a solid, and there might be phonons and other things that are, the electrons are radiating and they collide with defects. Okay, but we can think about it, a simple model. Let's just think about a gas of atoms that's sufficiently dense that they collide with one another. When they collide with one another, there's this phase jump. All right? Yeah.
And we can just, here you're assuming like they all have the same frequency.
That's right. Right now, I'm thinking it's kind of like a single mode, okay, of the radiator. So we're looking at that example for simplicity to start. Of course, this doesn't have, if I looked at the Fourier transform of this doesn't have one frequency because of these jumps, right? That's the broadening part when I think about collision broadening. Okay, so I can think about this thus as the total electric field that is coming from this ensemble of radiators. Yes, Donald, you have a question.
For the Fourier spectrum, if there's some mean free path, does that mean the spectrum, the frequencies we see besides the fundamental are somehow related to the fundamental?
That's right. So they will be, and we'll talk more about that in a few lectures. But if I were to look at this on some kind of spectrum analyzer, it would not be at this one frequency, omega, but would have a width that would be 1 over the rate of collisions, basically. Good. So, pardon me. So again, the point here is that my electric field, the total electric field that I see at some point in space is a superposition of all of these. And this is a random variable, which is just uniformly distributed around the unit circle, okay? And so I can write that as some complex amplitude, which is a random number, okay? So alpha is a random number, which is the sum of these unimodular complex numbers, okay? So we'd like to characterize the nature of the fluctuations, the means and fluctuations of this kind of field, okay? This is sometimes called chaotic light. Or natural light. Yeah. All right. But the point here now, so let's just think about what this complex amplitude, this phasor alpha is in this case. What it is the sum of unit vectors on the complex plane, okay? So, because each one of these is a unimodular complex number with magnitude 1 and some random phase. And so if I look at this on the phasor plane, the complex plane, then, you know, for in one of the sums, this might be, and then it might be that, 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 etc., etc. I'm just adding together all the unit vectors. Everyone see what I just did? So this is 1, 2, 3, 4, 5, 6, 7 oscillators, right? So for this particular set of phases that I tried to draw as unimodular things, this is alpha, right? It's the sum of all those guys. Okay? And it's got some magnitude and some phase, right? So this thing, you know, has some magnitude, and then there's some overall, you know, phase, the argument of that, right? Okay, so we want to assign a probability distribution to that complex number. Yeah?
It's separate from the double pendulum problem because all the oscillators are in phase with each other at the same period.
Well, I mean, this is not a double pendulum in any way. This is just a sum of many oscillators, which is random phases.
Okay.
So nothing is coupled to anything else. They're all independently radiating.
Okay.
There's no coupling between these oscillators. I'm just looking at the superposition of the electric fields that are radiated by all the radiators. Okay. Yeah. Good. So what our goal now is to ask, what is the probability distribution of alpha on the complex plane? This is, I can think about this as, you know, the probability of the real part of alpha and the imaginary part. So it's a function of those two, or its magnitude and its phase. Okay. What do you think? What is that probability distribution?
Gaussian.
Gaussian. Why do you think it's Gaussian?
Yes.
It's an excellent guess. If you want to guess something. But yes, I heard some other.
Because a bunch of things are happening.
Yeah, and I heard
Central limit.
the central limit theorem. So in the limit as n goes to infinity, this is a random walk. In 2D, right? So that's what I'm doing. I take the usual random walk in 1D is I take a unit thing and can go to the right, to the left with some, here I'm going in 2D with some fixed length 1, and I'm just randomly going in a random direction. And if I added all that up, that's like a 2D random walk. Everyone clear on that? And we all know, we've studied, I hope, the notion of random walks from statistics that the distribution of how far you'll be from the origin is a Gaussian in that case, and that follows, as Donald reminded us, from the central limit theorem, okay? So from that, what this tells me is that there is, and since this is isotropic, there's no bias as to whether I move along this direction or that, it's going to be rotationally symmetric. So whatever it's a Gaussian centered at the origin, and I'll just write the real part of alpha squared over 2 sigma squared. Everyone has their Deutsch mark and remembers this. This is the Gaussian, this is for the real part, and this is for the imaginary part. And they have the same width, and their mean is 0. That's to say the mean, it's on average, alpha is at the origin, but there's some fluctuation around that, okay? So that's just from the fact that this is a random walk in 2D, that's isotropic, okay? Or I can equivalently write this as 1 over 2 pi sigma squared e to the minus the magnitude of the complex number over 2 sigma squared. Okay?
And you didn't use central limit there, maybe you just said because it's a random walk in 2D, we know it has to be this way.
Only for n gets bigger. I use
When n
central
goes-
and it goes to infinity.
Okay.
Then this is true. So n large. Otherwise, it's not. I mean, the Gaussian, it only gets in the limit of many, many, many walks. Okay, so good. Right. So now the question is, what is sigma squared? That's the only thing that characterizes this probability distribution. Well, sigma squared is related to, in this case, if I integrate over the complex plane, and what I mean by this is, when I say d squared alpha, I mean d real alpha, d imaginary alpha. It's a unit of integration measure on the complex plane, like dx dp. Times this probability distribution. That integral is fairly easy to do, and when you do it, you get 2 sigma squared. Okay. So this is that, okay, but still, what is this telling me? This is telling me the mean distance the walker is away from the origin squared. Okay. So this is the mean distance, that's to say, what is the length of this vector squared on average? Okay? And what is the answer if I take n random walks? No, the mean is 0, but the square is not 0. Which is to say, if I were to look at the square root of this, do you remember this from a random walk? What is the fluctuation of the walker? Root n. Therefore, the square, it's n. That's the fluctuate rate. Okay. So, good. So we have now defined this probability distribution. No, in 2D, this is 2 squared. This is the mean distance squared, which is n. So this is equal to 1 over pi, the number of oscillators, e to the minus alpha squared over n. Okay, so yeah, very good. So and so for this what we have is that the mean, I'll put a bar here to, as opposed to a expectation value to distinguish this from the quantum expectation value. It's the same thing, which is this, is equal to n, okay? And the mean alpha is that's equal to the mean of x plus mean of p.
Wait, how are you replacing that when it's only true in the limit when n goes to infinity?
Because I'm only looking at ending.
Okay.
I'm only looking at the ending. Then this is a good approximation. I have an Avogadro's number of oscillators. I'm fine with 10 to the 23. All right, good. All right, so let's see. Let me remind myself what I want to say here. Very good. So let's just think about, how should we understand a little bit more about the nature of this fluctuating light? So I want to think about the intensity of the electromagnetic wave. Okay, so I'm just going to call the intensity without squared as the square of the amplitude. Okay, the square of the complex amplitude. Everything here is a complex amplitude that is writing. Okay, and the square of the complex amplitude is E0 squared times the magnitude of alpha squared. Okay, so what this says, firstly, is that the mean intensity in this case is n times E0 squared, because the mean of this, what you said, was n. Does that seem right? Or does that seem wrong?
We're taking n to be very big.
Yeah, that's fine. There's a macroscopic amount. It's really, what I'm asking is, does this scaling, the fact that the intensity is proportional to n, make sense? And not n squared?
Incoherent?
Incoherent. If I had n oscillators all in phase with one another, then the electric field here would be equal to n E naught. And the intensity would be n squared E naught, because there is constructive interference. So when I have coherent oscillators, then I should expect the intensity should grow with the square, because the field adds up. The field grows linearly, but the intensity would grow. So this is for coherent oscillators, where they have these nice, well-defined phases. Here, because of the randomness of this, we don't add the fields, we add the intensities, right? So because they're incoherent. So here we added the fields, and here we added the intensities. That's the average intensity. But what about the fluctuations in intensity? Intensity is not perfectly well defined because the magnitude of alpha squared is not definite. It obeys this probability distribution. So I want to turn this probability distribution into a distribution of intensities. So how will I do that? I'll just change variables. We have here I, so let's just change variables, right? So that tells me that alpha squared is equal to I over E naught squared. That's fine. So I'll put that in here, but then I need to change, to get a probability density, I need to change the measure of integration, because I'm integrating no longer over the two quadratures, but over the magnitude, okay? So what this tells me is that d alpha squared, which is the magnitude of alpha d 2 times that, by our good friend calculus, is equal to di over e naught, okay? So that tells me that d squared p of alpha is equal to, well, firstly, I need to think about this, d alpha, in terms of not the real and imaginary parts of the complex number, but in terms of its magnitude. And in particular, what I'm looking at here is I'm interested in everything that has the same magnitude. What I'm really looking at is a probability distribution within a particular annulus, a d magnitude of alpha, because that's the d of the intensity. Yep.
Is it di over e naught squared or just d?
No, over e naught squared. Yeah, yes, absolutely. E naught squared. Thank you. Very good. All right, so this, if I'm only interested in the magnitude, is 2 pi alpha d alpha. That's the area of that annulus. The perimeter is 2 pi alpha d alpha. That's the area times e to the minus alpha squared over n pi n. But 2 times alpha d alpha is equal to, so the pi's cancel here, di e to the minus I over n e naught squared over n e naught squared. Okay? Yes?
So we already did the phase integral.
Yes, so I'm looking at all the points that have the same magnitude. So that's what I mean when I'm looking at the intensity. We're looking at not at the phase, but just the amplitude to get the distribution of intensities. Okay? So this here is the probability distribution of intensities. Okay? So first question, just from this I can calculate, so this is what I'm calling P of I, probability of having a particular intensity. Okay, it's distributed exponentially because the other thing was a Gaussian, but that's, in terms of the intensity, that's an exponential function. So the mean intensity, the I goes from 0 to infinity, that's the magnitude, that's the, goes from 0 to infinity, P of I. So that's that, which, as before, if you do that integral, is what we just said before, is that. It's the same thing we just got before, okay? Up here. That's fine. So I can also write the probability distribution thus as 1 over the mean intensity e to the minus I over the mean intensity. And what about the fluctuations in the intensity? So let's calculate the moment I to the n. The probability distribution. Okay. That's an integral you can do. And the answer is n factorial times I bar to the n. Okay, that's an integral you can do. So that's a lot of fluctuations. In particular, the mean of I squared is twice the mean of I squared. Okay, when n is 2. Which tells me the fluctuation in intensity, the variance, which is the mean of I squared minus the mean of I squared, is equal to I squared. Yeah,
Why are we looking at the case only for n equals 2?
because that's the first thing of interest. I'm interested in the fluctuations. That's the first order moment I would always look at.
But isn't a lot of what we found here dependent on n being very, very low?
Oh, excuse me, there's many different n's. N here is the number of oscillators.
I
Okay?
see.
This n is just a moment of the distribution. It has nothing to do with the number of oscillators. I'm just asking about what is the mean of I squared and what is, it's nothing to do with that n. Yep. So that's a lot of fluctuations. Okay, so the light, if you were to put light from a lamp, a flame, or look at the light from the sun on a what is it called? Yeah, but there's a square law detector, something that measures the intensity. You would see it being fluctuating all over the place. Okay, with a fluctuation that depends, goes like this, it just is equal to the square of the intensity itself. So this is a very highly fluctuating source. These kinds of this natural light sources, like from a flame. Even if I could put it through a narrow bandpass filter, so it has a definite frequency. Okay, so that's some of the things we're going to start with. So now the next question I want to ask is, what is the quantum mechanical description of this kind of light? Okay, in the same way that we said a perfectly well-defining oscillator had a state. If we had a coherent oscillator, then the state of the quantum field is what? A coherent state. Okay? So we would say that if we knew it was a coherent oscillator, it had a definite complex amplitude, it had a definite field complex phasor, and we would say that the state of the quantum field is this, okay? If I have an incoherent oscillator, that's an incoherent field, with some probability distribution. I don't know what alpha is. I can only assign a probability. Alpha might be 0. It might be 1 plus 3i. It might be whatever it is. But I know I assign a probability distribution to that complex amplitude. And in particular, I'm going to assign this probability distribution to the complex amplitude for this particular model of the field. What is the state of the quantum field in that case?
Mixed state?
Yes. And how would I write down that mixed state?
Weighted by the probability distribution function.
So I would say I have a statistical mixture, or sometimes known as a convex combination of coherent states. If I had this is the state of this case. In this case, rho is that, okay? So I'd write, that's a pure state.
It's not, it's a mixed state.
Even though it's a Brockhead, it's still a pure state. Because there's only one
I see. It's not
wave, or one ket, or one state vector in Hilbert space that defines it. It's just another way of writing the state. This state is a mixed state, generally, unless n is 1. Yeah. Okay? So, well, that wouldn't make sense at all because it only would random infinity. So, this is the quantum description of the incoherent light field where P is an honest-to-God probability distribution. Okay? And that is what we're going to define as classical light. Classical light is some statistical mixture of coherent states. If I try to write whatever other state I had in this way, and I found that P was not positive, was highly singular, was some crazy asked function, excuse me, then that would be a signature that this state is not describable as a statistical mixture of parents. We would call such a state non-classical, okay? And this, in general, we can try to write any state, whether it's classical or not, in this way. This P, if this is true, this is a real probability. More generally, P of alpha is known as the Glauber-Sudarshan P representation. It's an example of a phase space representation of the field. We'll talk about many such kinds of representations next semester, like the Wigner function is another famous phase space representation. This is one of the phase space representations. The first one that was written down in quantum optics context. Okay? Yes?
So if P is a delta function, like
Yep.
an actual delta function,
Yep.
then it is.
That's a fine
That's
probability
classical.
distribution. It's just the limit of something that,
Yeah.
and that's a good. A delta function's fine. A statistical mixture that has only one element is still a fine state, and we call this classical light too. Okay? So, fine. All right, but just because the state we're calling classical light doesn't mean everything we measure now is going to have a definite outcome, because in addition to the fluctuations that we just described that came from the fluctuations in what the coherent state is, there will be other fluctuations due to quantum fluctuations, right? So there's both now classical fluctuations coming from the fact that I don't know what alpha is, and quantum fluctuations due to the fact that not everything I measure is an eigenstate. This is an eigenstate thereof. For example, let's look at the number fluctuations, okay? So if I look at this state and I want to know, in general, if I have a state of this form, and I want to ask, what is the mean number of photons in this field? So now, this is a quantum expectation value, and the way I do that is I take the trace of n with the density operator, right? Which is equal to the trace, if I take this form of the density operator, right? And this is A dagger A, so this is alpha squared. So it's just what we had before. This is the mean of alpha squared, which for our case was equal to the number of oscillators. That's what we just had before, okay? But let's ask about the fluctuation in the photon number for this state. So let's now calculate the mean of n squared, and then we'll subtract from it the mean of n squared, okay? So this is equal to, I'll just take the trace and write it, give alpha, n, and I'll write n squared out, a dagger a times a dagger a. Okay, you with me? How do I calculate this? Commutators. Whenever you're taking expectation values with coherent states, you want to commute into normal order. Put all the a daggers on the left, all the a's on the right. So I'm going to replace this by a dagger a plus its commutator, which is 1. Okay? And so this is equal to the integral over the probability distribution, alpha, and now everything here is in normal order. And then this is back to the mean n. Right? That term with the 1 is just the mean of n. Okay? So this is alpha star times alpha star, alpha alpha. So this is alpha to the 4th. Okay? So what I see here, we'll come back to this, is this is the mean of alpha to the 4th plus n. Where this bar is this integral, integrating over that probability distribution. So, of course, we just said here, this is the mean of n, so I can write the fluctuation in n as the mean of alpha to the 4th minus the mean of alpha squared, because that's another way of writing n squared. I'm going back and forth between writing the mean of n as the mean of the amplitude squared and the mean of n. I'm using both of those interchangeably for a reason. What do I see here? What I see here is that this is equal to the mean n plus the fluctuation in alpha squared, right? The fluctuation alpha squared is the mean of alpha squared squared minus the mean of alpha squared squared, right? What is this? These are the intensity fluctuations. What we just talked about, right? The magnitude squared of alpha is the intensity. So there are two contributions that are coming from this. In fact, these integrals we can do. They're the same integrals I did over there. I just didn't write them out because I wanted to emphasize this point. This guy is equal to the 2 of n squared, okay? So this whole thing is equal to let's put this together. Over here, I said the fluctuations in intensity was equal to the mean intensity squared. In the quantum language, the fluctuation in the amplitude intensity is the mean of n squared, because n is like the intensity, right? So what I see in this derivation that we did is that there are two contributions to the fluctuations in the number of photons in this field. One fluctuation came from the fact that this wasn't a coherent field. And because the intensity is fluctuating, the number of photons in the field is fluctuating. And from shot to shot, it'll be something else. And those intensity fluctuations are that. However, there's another source which had to do with, even if I had a perfect restabled laser with a definite alpha, with no line, with no nothing, it was perfect, I would still see a fluctuation in the photon number, and that's this. These were the Poisson fluctuations. So even if there were no fluctuations in alpha, if I had the pure state, the delta function distribution that Tristan suggested, I would still see fluctuations because of quantum noise. There's two kind of problems. There's sort of the quantum noise and the classical noise, and they both contribute. But what it's saying is that if I have a classical source, this is always greater than n. We would say the fluctuations are super Poissonian. So a classical source always has, at minimum, Poisson fluctuations. A classical source could have more extra fluctuations due to the fact that the amplitude is fluctuating, and those, we call that having super Poissonian fluctuations. Okay. Yeah.
How did you evaluate that integral without knowing what P of alpha was? You just said.
No, I'm using this P of alpha. The same
I
one.
see.
I'm using the same one. Yeah. I'm not.
Use that, right?
Otherwise, it would be some I couldn't do it. I'm sorry. This is only for this particular P of alpha. Everything I'm looking at right now is for that particular state. Yeah. Very good. So that's interesting. But wait, there's still more. How much would you pay? No. If I think about this, so what we just sort of looked at this is in a kind of wave picture. We thought about our state as a statistical mixture of coherent states. Each coherent state is kind of like a classical wave. But I can perfectly well express this in the number basis. Okay? So I can substitute in how do I express a coherent state as a superposition of number states? What are the coefficients? Yeah, what are they? E to the minus alpha squared over 2, alpha to the n over the square root of n factorial n. You will memorize this. Okay, that's my hypnotic suggestion. All right, good. You're gonna come at it when I'm like, you gotta memorize that. That's just something that's like, maximum equations. All right, good. So I substitute that in for that, and I do the integral. I think that's something for homework. And you find the following, that for this, given this Gaussian distribution, the one over here, so P of alpha here is equal to 1 over n, which is this mean number of photons, e to the minus alpha squared over n. Okay, that's what we found. Capital N is equal to the mean number of photons in this case. I substitute that into this expression, and I get something amazing. Okay, so this state which was given by this ensemble of collision-broadened oscillators, which had a Gaussian distribution of alpha, is equally well thought of as a statistical mixture of number states. Or Fox states. Remember, the ensemble decomposition is not unique. there are many different ensembles which, when I statistically mix them together, are exactly the same state, okay? And this state, as seen in homework, is the same as that one, okay? So I can think about my distribution equally well as a statistical mixture of number states, a state that doesn't have a definite number of photons. It has an uncertain number of photons, not in a coherent superposition. There is no coherence between the different number states. In this case, it's just a pure diagonal matrix in the number basis. This guy will have off-diagonal elements in the number because it is a coherent superposition. This is a statistical mixture. Okay? This distribution is well known to those who know it well. That's one of my favorite sayings. It is known as a Bose-Einstein distribution. Because it comes out in a completely different way from thermal physics. It is the distribution of photons in a thermal state. Did you study this yet, Professor Dunbar?
The preface to the book.
He's been
Yeah.
teasing it for a while.
All right. So let us just, you're doing this for homework, but let me just say a few words about it. So this is the distribution of photons in a thermal state. What do I mean by thermal state? A thermal state is a state at a particular temperature. It's also a mixed state, okay? So if I have a system at temperature T, then I can use the canonical ensemble to write down the state and thus the density matrix in terms of the energy eigenstates. And as an operator, it looks like this. Okay? Where Z is the trace of e to the minus IHT is our friend or enemy, the partition function. Okay? So that is a thermal state. For the case of a harmonic oscillator, where H is equal to I'll write it out. H bar omega A dagger A over K Boltzmann T, which in the number basis is equal to e to the minus n beta ht n. Where beta is defined to be 1 over K Boltzmann times the temperature. Okay. Now I claim that, so this is the probability of seeing n photons in that mode. Okay. Doesn't have a definite number of photons. It has a distribution of photons. This distribution is actually exactly the same as that. The first thing one has to do to relate those two is to calculate what the mean photon number is. So the mean photon, and you have to calculate the partition function. You have to, well, that's called your homework when you're doing that. And who remembers what the mean number of photons is for a thermal state? It's called the Planck distribution, right? Planck distribution, Planck derived and introduced his constant in perpetuity, Planck's constant, in order to get this right. And the answer is e to the h bar omega over kt, or beta That's the mean number of photons in a thermal state, which tells me that I can rewrite e to the minus beta h bar omega let's write this way, is equal to 1 over n plus 1, which is n plus 1 over n, which means e to the minus beta h bar omega is equal to mean n over mean n plus 1. And when I raise this to the nth power, I get this to the nth power, and when I put in the partition function, I get that. So this distribution is the same as a thermal state, as for a thermal state. So chaotic light is also known as a thermal state. It's all about the randomness in the system. So it's interesting, a thermal state has different characteristics. If I were to ask about its distribution of amplitudes, it would be Gaussian. So the thermal state is perfectly well defined by this. Okay, so this state is equal to this state, where this guy is a Gaussian. Equivalently, it's a superposition of, or not superposition, excuse me, a statistical mixture of number states with a Bose-Einstein distribution. And in fact, Einstein famously noted when you looked at how the fluctuations in this and found that it was this plus this, he understood this was the particle contribution and this is the wave contribution.
Are you missing a square?
No. So if I remember, this is the fluctuation photon number. There's a part that is coming from the fact that there are particles there, the Poisson distribution, right? That's this part. But the intensity distribution, the fact that the waves are fluctuating, was this. Okay? Very nice. All right. So, interesting. We have some different characteristics of this particular kind of light source. We just talked about a thermal light source, which is the classical light. At 0 temperature, that's a coherent state. Or, well, it could be the vacuum, depends. All right, so, so we've been talking about photons for a while. What evidence do we even have that photons exist? Photoelectric effect. That's what we learned, right? So we learned, in fact, Einstein famously won the Nobel Prize, I think it was 1925, I don't remember, maybe 100 years ago, for the photoelectric effect, not for relativity. Interestingly, that was a very political thing here. But so we're taught about the photoelectric effect as the thing that and in the photoelectric effect, what we do is we have some material and we shine light on it, and photoelectrons are ejected. Right? And famously, if you look at the kinetic energy of the photons as a function of the frequency of the light that is shined upon this material, then we find that below some cutoff, there's no photoelectrons at all, and then the kinetic energy grows linearly. It's proportional to the frequency. And this is explained by saying there are these corpuscular particles that come in, and unless they have enough energy, that the energy is actually, there's a particle with energy h bar omega, and there's an energy here which is sometimes called the work function, below which the photon doesn't have enough energy. I mean, energy in classical electromagnetism doesn't depend on the frequency, it depends on the amplitude, right? And we have the Poynting vector, we have the flux of energy, it has nothing to do with the frequency. But in this case, I'm breaking this up into these pieces, these chunks, h bar omega, and that gives me, it's an explanation of the photoelectric effect.
And,
What?
and explanation.
Yes, exactly. So what I'm here to tell you is, forget it. We don't need no stinking photons to explain the photoelectric effect. What we need, in other words, I don't have to quantize the field to perfectly well define the photoelectric effect. What I need is that the matter only absorbs light in a particular way. So I can have a particular model for this. Let's just think about photoelectric effect just in terms of ionization of an atom. So I have some atom with energy level structure, and there's an ionization threshold, okay? So this is the ground state. These are different excited states. This is my ionization threshold. Okay? And now I'm going to shine light on this with some frequency. And I can think about, okay, there's an energy associated with that, h bar omega. But I'm just not saying it's a photon, I'm saying there's an energy associated with that frequency. And up here is some continuum of states, right? There's some particular energy here, but there's a density of states, because this is the continuum. I can't talk about one state, I talk about states within a particular energy range. So there's a ground state, and there's some particular excited state. Okay? Now, I ask you, those of you who everyone has taken graduate quantum mechanics, or maybe your undergraduate class, or maybe in your free reading, and you wanted to calculate what is the rate at which this thing ionizes, how would you do it?
What is Fermi's golden rule?
Yes, Fermi's golden rule. It tells me the rate of absorption, which is then the rate of ionization. Is given by, well, I need to think about what the interaction Hamiltonian is. So there's an interaction between the light and the matter. And to the degree that I can use the dipole approximation as a decent approximation, then, you know, this interaction is minus d dot E, where I'm going to treat E classically. I'm not going to quantize the field, but I'm going to say there is an oscillating electric field, which has a positive frequency component and a negative frequency component. And you do the whole rigmarole of time-dependent perturbation theory, and you find that the rate of ionization here is given by 2 pi over h bar. The matrix element of the positive frequency component squared, because that's the thing that leads to absorption, times the density of states where the energy of the excited state is equal to the energy of the ground state plus h bar omega. Now I want to emphasize here, I did not put a hat on that E. This does not require a quantum description of the field at all. It's just that I have a time-dependent oscillating force on the atoms, and that force causes this transition, and when you do time-dependent perturbation theory, under the conditions that this interaction Hamiltonian is a small perturbation compared to the binding electron, this is what you get. The h bar omega comes in because h bar is in Schrodinger's equation, and omega is in the time dependence of your field, but not because I quantize the field at all. So you can go back somewhere in your textbook or your notes where you derived this and find that you never quantized the field when you looked at the absorption. Yeah.
So, is there a meaningful regime where this perturbation theory doesn't hold anymore, and we need quantum mechanics?
Well, the breakdown of perturbation theory is not where the quantum mechanics will break down. I mean, it's not where I'll need the quantum field to. We're going to come to the question of under what observations do I make that require me to have a quantum description of the field. What I'm claiming is that this is not one of them. I can perfectly well describe this observation. The kinetic energy here of the electron is equal to h bar omega minus the ionization threshold. This kinetic energy grows linearly with frequency. That's what this cutoff is. And if I'm below the ionization threshold, I see nothing. I can get this observation, this empirical measurement does not require me to have a corpuscular quantum nature of the light. It just has to say that the atom absorbs in these units. And in fact, you know, before the Compton effect in 1927, I think the physics community did not think about the photon as a real thing. It was a convenience, but not an actual particle. When there was a collision seen, a billboard collision between an X-ray electron and they saw that, they said, oh yeah, the Compton effect, there's a real particle there. That was really a first. You couldn't get that from a classical description. 27. Yeah.
That's 2 years from now.
I'm from the 1900s.
Dirac equation was 25.
Yeah.
This year is the 100-year anniversary.
Yeah, that was as later. No, the 25 is Heisenberg, matrix mechanics, and the Schrödinger equation. Dirac is later.
Schrödinger equation was 25.
Yeah.
Schrödinger was 27. Heisenberg 25.
Yeah, they were close. I mean, they were good. Yeah, yeah.
It's funny to think of photons being used as
So, you know,
cinema
there's the
oscillators.
old quantum mechanics. I mean, you know, you guys are 20-ish. You know, Dirac, I mean, Planck was 1898, right? It was around 1900, yeah, I think is when it was finally, you know, 1900, okay? Until Heisenberg, 25. There was 25 years of the old quantum mechanics where people were seeing observations, they saw the electron, they saw the, you know, the Bohr atom and so forth, but that whole thing wasn't really fleshed out for a long time, right? It's good to calibrate history by your life. You kind of know what 20 feels like. Right. I know what older feels like. Anyway, yeah.
Would it be fair to say that people use the photon as a way to explain things in a similar way to how we use simple harmonic oscillator to model things?
Yeah, I mean, it was a convenient mathematical thing, but whether the physical entity. So, what this is saying is that I can explain the photoelectric effect in a semi-classical theory. Quantum matter, classical light. In fact, that's how Dirac thought about black body radiation, that the oscillators somehow absorbed and emitted in this way, but that the light itself wasn't composed of these chunks. Yeah?
Did you mention that there was another example of particleness, whereas someone just left an experiment running with a super low intensity? So we saw-
Yeah, we're gonna get to that stuff. We're gonna get to that stuff, yeah. Okay, so,
Some grad students.
Okay, mind is blown. Bubbles are burst. So let's think about empirically then the following thing. If I take light, let's say it's a laser beam. It's a very well-defined field with a well-defined intensity, not thermal light. It's a stabilized laser. And I send it onto a photodetector. And this photodetector, this is very low intensity. Sufficiently low that I can have a single photon detector. Something that it might be a photo avalanche diode, where one electron that's photo ionized causes a cascade and gives me a click, okay? And so I'm in this Geiger mode, okay? What am I gonna see as a function of time on this detector? As I send this perfectly stable intensity on this thing. I'm gonna see click, 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 click. I'm gonna see clicks at random times. Okay? So there is randomness here in the photoionization process. So another assumption I have to make in order to explain, to use a semi-classical theory, is that this process is a quantum jump. Okay? As Bohr considered it, where things jump between energy levels. And another assumption of semi-classical theory is that quantum jumps are random, uncorrelated events. Under that assumption, as Andy was suggesting, these things happen according to a Poisson process. A Poisson process is a stochastic process which I have random, uncorrelated counts. That the probability of seeing the next count has nothing to do with how many counts I came before, okay? So that's the fundamental assumption of a Poisson distribution, that there's no correlation between that, okay? So Poisson, let me define n of t as equal to the number of counts in the interval between 0 and t, okay? This is a random variable. And let me just call n a comma b as the number of counts in the interval between TA and TB. So if this is a Poisson process, then there's no correlation. That's to say that this is equal to, if, let's say, this time is bigger than TB. Which is to say, if I have this condition of no correlation, what it's saying is that the number of counts in any two intervals, time intervals, that don't overlap is uncorrelated. So the number of clicks I see in this interval is not in any way statistically connected to that interval. Those two are completely separate. No matter any two intervals I choose, as long as they're not overlapping, they're completely statistically independent. That is what defines a Poisson process. Okay. What I want to now show is that the probability of seeing n counts in any finite interval obeys a Poisson distribution. Okay, a Poisson process is a stochastic process where I have a random variable that is a function of time. That's what I mean by stochastic process. And then I want to show that this conditions give me the Poisson distribution. Okay, there's another feature that defines a Poisson distribution is that there is a rate of counts. And what I mean by the rate of counts is that the mean number of counts in any time interval t is just proportional to t. Okay? So no matter what time interval I have, I ask what's the mean number? It's proportional with the same proportionality constant. So lambda is the rate. Okay? So with that, we can derive the Poisson distribution. Well, it's a little too late, so I'm going to do that next time. But what we will find thus is that the probability of seeing n photons in a given time interval will be equal to e to the minus lambda t times lambda t to the n over n factorial. This is what we want to derive. Okay? This is saying this is a Poisson distribution. With mean given by that. Once you have the mean, you have the whole distribution. Which is to say, if I thought about this photo counter, I would find that on average, the number of photons would be given by the rate times the t, but in each time interval of equal length, I'll see a different number of photons. So from shot to shot, I will see a different number of counts. That is known as shot noise. The shot noise is due to the fact that the electrons are corpuscular and you don't see a definite number of them because of this random ionization process. Okay? And because that ionization is completely uncorrelated, it's going to be Poisson. Just quickly, what is the rate in this case if I have an intensity here? That rate would be the rate at which photons are incident on this detector. What is the rate, if I have a certain intensity, what is the rate at which photons are, well, let's say this thing has a cross-sectional area A, then the power, the energy per unit time that is passing through this area is what? I times A is the flux of the intensity of the power. divided by h bar omega. This is the rate at which photons are hitting this detector through this area, okay? Because each photon has energy h bar omega. The power divided by h bar omega is the rate at which photons. So what I would see here is that this thing would be proportional to the intensity up here. Say again?
Would that be the momentum of the photon?
Well, I mean, it is related to momentum, but I don't think that this is really the energy that matters. It's true that the energy and momentum are related by c, but it's not
I
really.
guess for power, I'm thinking per time.
Yeah, yeah. So, good. All right, so what we're going to do next time is derive this, remind us where the Poisson distribution happens. And what this is saying is that even though I have these discrete events that happen at random, I can completely explain that with a semi-classical theory if I say that the photoionization effects are. Now, of course, I just want to make it clear. We know for other reasons that there is a quantum description. So equivalently, I can think about this as the photons arriving at the detector with a Poisson is completely consistent with that. The Poisson distribution of input photons, if I had a perfectly efficient detector that turned every photon into an electron, a perfectly quantum efficient detector, I would also see Poisson statistics due to the quantum fluctuations. So this is completely consistent with the quantum fluctuations of classical light. But I don't need that. It's not, this is what we call classical light. There's no quantumness that's useful in any way here. Yeah?
So, obviously we need to quantize the field to get that fluctuation.
Yeah, that's one thing we'll need, but we're going to talk about other, yeah, and we'll talk about that next week. All right. Let's call it quits.
Yes.